Hello students, welcome to this third lecture of the length measurement. In this lecture, we are going to discuss about a spherometer, and this instrument, which is also based on the screw system, is used to find out the radius of curvature of the spherical surfaces. Say for example, I have this lens with me, which is a plano-convex lens. It has the lower surface is plane and has the upper surface a spherical one. If I want to know the radius of curvature, we use instrument which we call as the spherometer, and this is an instrument which is a spherometer. So let's first of all try to understand what are the parts of this spherometer. So students, by now you have understood that whenever we are going to use any instrument, the very first thing we do is to find out its least count. How can we find out the least count of this spherometer? If you look at this, there are two scales. One is this vertical main scale and there is another circular scale here. Now if you look at this carefully, in the present spherometer which I have with me, there are 10 divisions on the lower side and 10 divisions on the upper side, and there is a zero mark here. And these divisions are in millimeter. That means I can write that the least count of main vertical scale is 1 mm, 1 millimeter. And if you look at the circular scale, there are divisions going from 0 to 100, and as we have seen in the screw gauge also, this 100 is not marked on the circular scale. After 90 we have directly the 100, because again it is a repetition, so we have 100 divisions. Now what you have to do is, you have to first of all take this circular scale 0 coinciding with the 0 of the main scale, and then give it one full rotation. And if you do that, you will find that your circular scale has moved up or moved down, depending on whether you are going clockwise or anti-clockwise. It has gone up or down by 1 millimeter. So if you have one full round which is equivalent to 1 millimeter, the least count of the spherometer is given as 1 millimeter, which is the pitch of this screw. Pitch means that the distance moved by the screw when one full round is complete, divided by the number of divisions we have on the circular scale, and this comes out to be 0.01 mm. Look at this. This has a similar least count as we have in case of the screw gauge. So students, now we are proceeding towards the actual measurement, and this time we are taking a plano-convex lens and we are interested to know the radius of curvature of this lens. For this, what we have to do is, we have to keep this spherometer symmetrical on the top of this lens, and we'll try to find out what is the height of the central point. Now if on the diagram it will look like this. This is the plano-convex lens and this is the topmost point here, and I'm interested to know how much is the height of this topmost point of the spherical surface from the base. Now let's complete this sphere to understand how we can calculate it. So if I complete the sphere, let me say this point is A and this point is B, and this is the center of the spherical surface. So joining A to O, B to O, these distances are nothing but they are radii of curvature of the spherical surface. What this theory will tell us, that how we can link the radius with this height h. We'll explain it later how to find out the value of the h. But let's say this is one parameter which we have to experimentally observe using a spherometer. If I say this point is C and I join this C from O, then this distance CO is equals to R minus H, because this height is H, so remaining one is R minus H. Whereas these distances AC and CB are assumed to be, say, the distance X. This is something which we have taken theoretically and will definitely remove it from our final expression later on. So let's take this right triangle and use Pythagoras theorem for it. If I do that, this will give me r square equals to, that is hypotenuse square is equals to base square x square r minus h whole square. This distance is x. Simplify it mathematically. Now this can be written as r square plus h square minus 2rh r square. So this r square is out. Take this 2rh on this side and this will be x square plus h square. So I can write the radius of curvature as x square plus h square divided by twice of h. Let me call this equation as equation number 1. Now the parameter which we have taken x cannot be determined directly. If I put it right, this is a spherical surface. If I am putting it in this way, I need to find out the distance from the central screw to the leg, which we difficult to measure. Instead, what we do is we try to measure the distance between the legs. By putting it on a piece of paper, they give the impression you join these points, and when you join these points, you are going to get an equilateral triangle. Let's say these points are P, Q and S, and this is our central screw. Let's say the distance between P and S and Q and P is L. Practically it may not be exactly equal. So if they are different, take L1, L2, L3 and divide it by 3 to find out the value of L. Practically we do it in this way. We try to find out this distance and this distance. They may be same, may not be same. So we take the average of it to find out this L. L we can measure easily. So now what I am doing is, I am trying to express this x in terms of L. How we can do it? Look at this. If I join S to this centroid point, so this distance is nothing but is equals to x. If I drop a normal here, this distance is L by 2. And as the property of equilateral triangle, the angle here is 30 degree. So we write cos of 30 degree. So this angle, that means the angle that is the central point. Let me call this point as, say, the Z point. So this angle Z, S and this one, say Y, is equal to 30 degree. So using this trigonometric relation, cos 30 degree is equals to the base L by 2 divided by the hypotenuse, that is equals to x. Or you can write x can be written as L by 2 cos of 30 degree. So that is L by 2 root 3 by 2, and that gives me L by root 3. So this is my equation number 2. Now what I do is, I'll put the value of x here in my equation number 1 to find out the expression for r. That is equals to x square, that is equals to L square by 3 plus h square divided by twice of h, which gives me r is equals to, if I simplify it, this is L square by 6h plus h by 2. So this is my expression to find out the radius of curvature. So try to understand what I have to get experimentally. Experimentally, I have to determine the value of L. I have to determine the value of H. Once we have these two values, we can put it in this equation and we get the value for the radius of curvature. So students, let's start the experimental observation. The first part, we are doing the measurement of the distance between the legs, that is the length L. For this, what all you have to do is, you have to keep the central pin slightly up and keep it on a plain paper, push it a bit. You will get the impression of these pins because the legs are sharpened at the bottom. So once you get it, you will just mark the circle on the top of it and join these circles with the help of the scale. And then you note down the length. That means the average length between the 3 points. After putting the impression on the piece of paper, you draw the circle around them and try to find out the length L1, L2 and L3. I did this impression here, and luckily all these observations are 30 mm. I am using the simple scale to find out this length L, and the least count of this scale is 1 millimeter. So all my observations are in millimeter. So the average value of the length, average length L comes out to be 30 mm. This is the first observation which we have to obtain from the spherometer. Students, now we are going for the second part of the observation. In this we have to make two main observations. First of all, we have to keep this plano-convex lens with a curved surface on the top and keep this spherometer in such a way that the ends of these legs, they are touching the curved surface, as well as the central screw also touches the curved surface. The next part is when you do the measurement with a plain glass plate. Again keep it and try to bring the central screw in contact with the plane surface. The first observation, I am saying this is observation X, and the second observation is observation Y. Here what we have to do is, we have to find out that what is the observation on the main scale, vertical 1, and observation on the circular scale. Then we have to add the two to get the exact value. Similarly, we have to repeat it for the plane surface. Take a paper strip, and once you feel that the central screw is almost in contact with the surface, you try to pass this paper strip from the bottom of the screw, and if you are able to get this freely from one side to another side, it means the screw is not in contact with the surface. In order to bring the central screw in contact, use the head and try to rotate it till you find that this strip is not able to cross the central screw. You will get the restriction here, right? But at the same time, you ensure that if you try to rotate the whole screw by giving a bit of the pressure, then it is not possible for you to rotate it easily. But if it is overdone somehow, say for example I am doing it a little bit more, right, than what is required, then you will notice that the moment you try to do it, first of all it is not stable, and then it will rotate by its own, taking a central one. This ensures that this is overdone, so try to bring it back till you find that the strip is not passing from the central screw, but our spherometer is stable. students, after making observation, the following data is obtained. We have taken 3 observations and we are able to calculate, as we have discussed, the H as 1.43, 1.46 and 1.46 in millimeter. When its average value is taken, it comes out to be 1.45 millimeter. Now rest of the calculation is simple. Using the expression which we have derived, the radius of curvature by this formula comes out to be 104.173 millimeter. We cannot go up to the decimal places of the millimeter, as we have taken the observation for the length L in millimeter. So our least count there was 1 millimeter. So we have to round it off to the first unit of a millimeter. So this value is 104 millimeter. Now you must have noticed that I have not discussed with you the zero error correction for this type of the calculation. Why we have not done it? This is also very important. It is because what we are doing is we are actually calculating the H by subtracting the value of X and Y. This X is the position of the circular scale and Y also is the position of the circular scale, but the difference is this is X is on the spherical surface and Y is on the flat surface. Suppose there is some error, let that error be delta. So what corrected value of X will be? The corrected value of the X will be X plus minus delta, and similarly Y dash is equals to Y plus minus delta. So when you do the subtraction, you will notice that whether the error is positive or negative, that will be out of the scene and there is no need to take the zero error. This is the say one of the advantage we have, because we are calculating by subtracting the 2 observations, right? So this is the point. However, we are able to get it to round off value 104. The measured value or the value given by the lens maker, he told us that the radius of curvature is 100 millimeter or 10 centimeter. So our error is there in the measurement of the radius of curvature, and that is equals to 4 millimeter, and percentage wise if we see, this is nearly about 4% error. So you can mention the error, but you have to round off first of all the value to the significant figure so that you can mention it, yes, we have measured by taking the least count up to the first unit of a millimeter. So friends, this is how we can use a spherometer. You may increase the number of observations in order to get better value for your measurement. Now in the next lecture, we are going to use the traveling microscope to find out the small distances, especially the orifice of a tube, where we are able to measure the diameter of that orifice, which we sometimes need in our experiments. So that will be the topic for the next lecture. So thanks a lot. Thanks very much for sharing your time. Thank you.